I would like first to thank EPMA for the kindness in inviting me to give this presentation at this important event. My presentation today will be divided in three areas. I will start with background of some important events in the region of the Heap process. I will discuss the present state of the art and the development of the present state of the art for raw materials, equipment, processes, and products, and as well as materials. And finally, I will take the risk of doing a 15-year scenario, what will happen in 15 years' time. I do that with the quite sure knowledge that in 15 years' time I will not be present at the 40 years anniversary of the EPMA, but who knows. I think it's in such an event as this, it's important to give credit to the companies and persons who have devoted their career work to the development, in this case of the Heap process. And the substantial work was started at the Battelle Memorial Institute, Columbus Laboratories in Ohio in 1955. And amongst the names which I found is Henry Seller, Edwin Hodge, Stanley Paprocki, and Russell Dayton. A tremendous lot of work was done on development of the heap equipment, on the powder to be used for the heaping process, and also on applications, both of semi-finished products and near-net shape products. And this process was in the beginning called gas pressure bonding, because we used it for pressure bonding of nuclear fuel elements. Initially, a hot wall heap was used with a maximum temperature of 830 degrees centigrade, a pressure of 69 megapascal. And this is, I think, is more curiosity. A lot of this material work was classified as secret. And one example is this invention by the same persons which I mentioned. It was filed in 1957, and the patent was granted in 1987. 30 years later, which is, there must be some reason behind that, of course. So by this way, they were able to keep the information confidential. But it has been studied before, reactions at high temperature and high pressures. And one such effort, development, was to manufacture synthetic diamonds. And there was a competition between ASEA Sweden and General Atomic in the United States. It started 1939, 1940. The processes, equipment was built, and I'm perhaps biased, but ASEA managed to manufacture in a Quintus press the first synthetic diamonds in 1953, a few months before General Atomic succeeded the same. The initial hot isostatic press were laboratory units, hot wall type, small sized with low productivity, limitations in temperature and pressure, was difficult to control the temperature, required highly skilled operators and brave operators, because not every experiment was successful, and some was to understand quite exciting. They used a monolithic pressure vessels with screw-threaded closure, which from a thermal fatigue point of view is a dangerous combination, and therefore the heap units were placed in bunkers for safety reasons. Then it's a pleasure to tell you more about this person, Mr. Baltzar von Platen. He's coming from a well-known Swedish engineering family. He lived between 1896 and 1985. He was a fascinating person. He wanted to be an opera singer, but failed. Then he was a deeply religious person. He wanted to be a reverend in the Swedish church, but failed. And after this failure, he had to take a Master of Science at the Technical University of Stockholm, Royal Institute of Technology, to which I'm located. And he, as a Master of Science thesis, together with a man called Carl Munter, managed to develop the modern cooler refrigerator, which you all use now. And they sold this invention and patent in material rights to a company called Electrolux, which you probably know, and was offered either 1 year's salary for an engineer or some krona per sold refrigerator or cooler. Mr. Munter, he took a few Swedish krona cooler, while Mr. Balzer von Platen took 1 year's salary. And that has been the way he had been working all his life. He has made excellent innovations, but some problems economically. He then managed to develop the synthetic diamonds, and for this industry, very now important, the wire wound presses, the Quintus system, together with ASEA, which is now used by Avure Technologies and others. And this shows the first patent from 1955. And you can see the frame of the equipment is wire wounded by high strength, cool deformed steel wires attacked with, which managed to give very good stability for the equipment. Important to know, if a monolithic shell is cracked, the hole will go through. If one of these wires is cracked, the load will be taken over by the surrounding wires. So this was a genius invention by Mr. Balzer von Platen. If you go back to the work of Battelle Institute, they made some very important developments in field of materials, near-net shape products. First, of course, I mentioned the synthetic diamonds, 1953. Battelle made also the nuclear fuel elements, beryllium products by powder metallurgy, which I haven't heard about since. Cemented carbide, pore closure of cemented carbide products, pore closure of aluminum castings, 1970 high-speed steel and tool steels, etc. I will give you some of the examples in the following. This shows beryllium products made by Battelle Memorial Institute. And I'm quite impressed of this. To the right you have bottles of beryllium. By making a compound product, beryllium layer upon a copper core, and then you dissolute away the copper and get the shell and bottle. So this shows that Battelle also very early stage worked with near-net shape processing. This shows the work from Kennametal, if it's possible to read. You can see the advantages of pore closure. Take away the last percentage of pores in cemented carbide. And you can see that the transfer rupture strength is increased by 20-30%. And this was further the basis for the development of the sinter heap process, which Leo Prakash has described. This is an exciting area where there was initially a very severe competition between Crucible Steel in USA and Stora, now Era Steel. And on the top you can see the cast structure conventional cast structure, the carbide segregation in ingot cast high-speed steels, and you can compare it with the fine microstructure or the as-atomized particles. This was presented the first time in 1970 here in London at a conference arranged by the Iron and Steel Institute. The important thing is that by the heaping process, this fine structure is remained from the as-atomized powders. And you can see the conventional bar forge, you have this carbide segregation and carbide layers. So by this, going for the powder to the powder metallurgy route, you gain two things. One was improved performance, for example, in cutting tools. Lifetime could increase 5 to 7 times. But the limiting property, material property of high-speed steel in tool steels is hot workability. And the hot workability is often addressed as area reduction. With high-speed steels, you have something often a hot workability reduction of area at high temperature of 20%, 20%. That is the limit of the hot workability. While on PM steel, you can have 80 to 90%. Very ductile. This is also the Damascene steel. It's manufactured by mixing two different types of martensitic steels and a special forging method, and you have the grinding of the sword, and you can then have an etching. You can see the structure. This structure is similar to a sword which was found in Sweden and was manufactured over 1,000 years ago. And you have here at the British Museum an excellent exhibition of the Vikings. But there is a misconception here in England. The Vikings were friendly, kind, nice, international traders and businessmen. Everything else is wrong. And please remember, they were my ancestors and relatives. Present state of the art. Go back 20 years, 25 years, the functional properties of, for example, high-speed steel, PM high-speed steel, and tool steels were quite good. But some properties, material properties, was not sufficiently good. Impact strength, fatigue. And the reason for that was that in PM steels, you have three types of oxide inclusions and other inclusions. You have from the slag, exogenous slags, furnace slags, ceramics, cheese sandwich, etc., which contaminate the powder. You have endogenous slag inclusions, that is desoxidation products. No one has seen this, so you don't have to bother about endogenous slags. But you also have surface oxides on the particles, both in water and gas atomized powders. And it was 20, 25 years ago, it was also a quality problem how to characterize the powder, how to make the quality control of the powder. I'm quite humble, so I don't mention the authors of the report, but it was studied in Sweden, and this curve shows the oxygen content as a function of the specific surface of the powder. Or another way, it's if you take 1 divided with the D, where D is the diameter of the powder, you get the same curve. So you can see that oxygen content of very fine particles, large specific surface was up to 500 ppm, and under 100 at very coarse particles and the bulk. And the companies at that time, when they stated the oxygen content of the powders, they took the very coarse powders, of course. So they stated often something under 100 ppm. But if you can see this as a straight line, which means that the surface thickness of the oxide layer on the particles is independent of the size of the particle, which is a very important finding for gas atomized powders, but not water atomized. And by taking this, measuring the oxygen content for two different size powders, you make a sieving experiments, and the particles which stuck in the sieve you take for analysis. Then you have a well-defined surface area, and you can find that when you approach it zero, you have the contents of exogenous slag inclusions, which are the dangerous one. And that has been used as quality control system, and also used for powder cleanliness. Traditional process originally was to have a small tonnage and filling it frequently, atomize and fill it again. This meant risk for exposure to air and high risk for contamination, and also the temperature in the tonnage went up and down. By the modern process, for example, the most modern plant is in Söderfors, you have a closed powder production. The tonnage contains the whole charge, 5 to 8 tons. You do some refinement in the tonnage, you get very low oxygen content. You have a heating system in the tonnage, so you get exactly the temperature which you want, and you collect the powder without exposing it to air. And then you get very low contents of exogenous slag inclusions and virtually no surface oxides. Regarding heap development, the heap units are now quite large. The largest can take a load of 30 tons, which is impressive. Cycle times has decreased from 24 hours to less than 12 hours. The number of cycles has decreased per year. The process control has improved. You can do heat treatment in a heap furnace, quenching, tempering, etc., and improve process economy. I'll come back to that. The direct process cost, including cost for labor, depreciation, and materials, was in 1998 about 0.9 euro per kilo if you have a full large heap, and now has decreased to 0.3 euro kilo. And also, this shows what I say is the economical feasibility area for different forming processes. The number of parts is, let's say, in order of components. And on the other scale, you have the weight of the part. And for heap, you have right now something from 20 kilos up to 30 tons. Minimum amount is 1. You can't come less. And then you have, let's say, 10,000 parts. And that is expanding. And also you can see the area for additive layer manufacturing fits in perfectly well in a field where powder metallurgy was not competitive earlier. This shows some recent equipment installations and modernization, 2 large heap units in Böhler, or the Holm Powder Technology in Kapfenberg, and charging. And the largest plant in Japan, in Metas Technology Limited. Length 4.2 meter, diameter 2.05 meters, temperature up to 1350 degrees centigrade, pressure 1180 bar, and the weight of the equipment is just 550 tons. Now I will talk about the possibilities of making alloy development in powder metallurgy. When I lecture in university about powder metallurgy. I said, this is unique technology. You can, when you do a conventional technology, you have to take consideration of the size of the parts, because small parts are laboratory scale and the properties are different than the full scale. So it takes very long time. But when you do powder metallurgy, you then do an experiment on a Monday, you do take the results on Wednesday, and you can use it for production on Friday. Because the scale you do in laboratory is the same scale as in the full plant, and that is unique. So, and also there is a possibility to what called alloy design for specific products applications. And this is an example of alloy design. It's a nitrogen alloyed tool steels for application where you have adhesive wear, where you have 1.8% nitrogen, which is obtained by solid state alloying of the powder. And you can see the other alloying element. And to that you get a 20 volume% of vanadium carbonitride with extreme hardness, and also chromium 6 carbides. You can see the structure is very nice. This is just one example I would like to stress out, is that normally if you have an alloy system and want to increase the hardness and tensile strength, you decrease the toughness and ductility. That's life. But if you manage to refine the structure, make it finer, you can both improve the properties. You can, with the same toughness, improve the hardness and strength. And you can see here with conventional manufacture, electroslag refining, and powder metallurgy, how you can improve the strength or hardness and ductility for the same alloy by changing process method. This is publication with unique material. I mentioned there are limitations when you do the casting and forging. There is an interest for storage of nuclear waste or protection against radiation to add boron in the steel. And to the left you can see what's produced as best with conventional casting and forging technology is 1.2% boron. And to the right you can see PM Heap with 1.8% boron and very nice even structure, easily forged. And this I've added because, as you can see, the first time I've ever heard about this recent publication, a new Newton-absorbing steel with 2.25% boron and addition of gadolinium. Have none of you used that earlier in your products? But this gadolinium has excellent properties for nuclear absorption of neutrons. This is also was published just 2 months ago. I think an excellent example of alloy design for a certain application. This is a material from Sandvik Heating Technology, Kanthal, called APMT. It's a powder metallurgy used product. It's dispersed and strengthened, probably with something like EPMA. And it's designed in such a way that when oxidized, it's not forming a chromia oxide film, but alumina oxide film. This means that the strength is improved by the dispersion hardening of this FECR alloy, with high creep strength and form stability, and the alumina surface layer gives protection in oxidizing, sulfidizing, carburizing, and reducing atmosphere. It now can be produced in sheets, tubes, strips, and wires, which means the conventional limitation in sinter steel production you have often the furnace limit to 1100, 1120 degrees centigrades. You now can build continuous furnaces running at 1250 degrees centigrades. I will show you some example of the near-net shape technology, which is coming, expanding. This for Synatec in the United States, a PM Heap superalloy, impeller, body coat hot isostatic pressing A-beam, Sweden, and body coat is the leading tall heap manufacturer in the world and also has the largest production of near-net shape heap products. And this from ATI, a similar product, but also you can notice on the part there, you can see it has an internal cladding. So it's also compound material. So if you summarize, so the powders now used is very much better than for 20 years ago. For the same alloy system with the same designation you have 2014 and compared with something from 1980, you have improved properties, strongly improved functional material properties. You have low oxygen content, high cleanliness. This gives good mechanical properties, as good, often better than cast and forged. And I would like to say comparable, but often better corrosion properties to forged materials. In some fields where you have offshore equipment, you have special corrosion problem and cracking problem called a hydrogen-induced stress cracking, which you don't have with PE material. The advantages is listed here, but I would like to stress out one. It's a shorter lead time. It takes perhaps from order to delivery 1/3 compared with if you have to make a casting, forge it, machine it, and deliver. And the isotropic properties mentioned here is also essential because they enable you, the manufacturer, to make ultrasound testing to see if there are any cracks, porosity, etc. With a large advantage. Makes safety when you have the product. Then I will talk a little bit about 15-year scenario. And I would like to start with the disclaimer and quote the Swedish unknown author Axel Wallengren. He is well known under the pseudonym Falstaff Fakir, who in 1896 said, "It is difficult to foresee, especially about the future." And so I will take a risk anyway. The powder metallurgy over inert gas atomized powder or PrEP or REP atomized powders give numerous advantages. You can use new alloy system based on solid state alloying. I mentioned tool steels with nitrogen alloying. You can also have interest for high alloy stainless steels. Nitrogen high alloy stainless steel is an interesting product. To take away nickel, you can add nitrogen. And the interesting thing is that when you do this solid state alloying of the powder, you get a thin layer of nitrogen on the surface, but during the heaping process, you get a very nice homogenization through the ingot. You have dispersion strengths in alloys. I mentioned stainless steel applications with high boron content. We have a tremendous lot of nuclear waste to take care of. Components with compound structure. And also, which I mentioned some example, potential to develop new alloy systems with functional properties oriented for certain fields of applications. With present process metallurgy, you are limited by, for example, hot workability, cold formability. You can virtually avoid that by the PM route. Further development of the equipment itself with heat treatment ability, quenching hardening, case hardening, and tempering. What I was thinking about when I brought this is that for conventional sintered steels, you have a density now with high pressing, which is quite close to getting close porosity. You're quite nearly close porosity. If you increase the temperature somewhat and have high pressure, you will come to a situation with close porosity, and then you can get manufactured parts with full density. You will need some grinding, of course, but to fix the tolerances. But I could see that a sinter heap for steel products will be coming. The same will be for heap units, conventional heap units dedicated for pour closure of metal injection molded, already done, additive layer manufacturing, and conventional uniaxial pressing. The third is a little bit the last is a little bit speculation. If you look on a plant where you have production of high alloyed steels, which are difficult to cast, you can't use continuous casting. You have to do ingot casting. The yield you have of such a product by casting, forging to the semi-finished product is quite low. And with new modern heap units, inert gas atomization, you will be able to do it competitively by the heap process route. So my conclusions. The world market for products manufactured by heap or metal powders will expand rapidly during the forthcoming 2 decades due to a number of reasons: improved process technology, and we are already there with improved process technology, especially, for example, for the powder production. New and larger production plants with the latest manufacturing technologies. There are already some heap-based production plants, and developments of new high alloyed and high performance PM steel grades for certain fields of application, new near net shape applications, pore closure, and then I finally want to stress out, to enable this fast development of new applications, profitable markets, we need standards. And EPMA had to work for development of standard developments so the product will be able to be sold on the market. Thank you very much.